Hello everyone. In the last session, we looked into the introduction of finite element method and its procedures. Then we moved into the derivation of the stiffness matrices of bar element in which the load is actually applied. And then we did an example where you solved for the displacements and forces of a system. Today, we're going to look into truss elements where bar elements can be oriented in any direction to the horizontal or the vertical axis. For example, let's say we have a truss and we can label these nodes as, let's say this is A, this is B, C, and D. Now you can see here that each of these elements is oriented to the horizontal axis by a certain angle. Now these angles vary with each element, and in these elements, since they are bar elements, these elements will only have axial forces. Now if we look at AD, which is this one, and AC, then you'll see that the force acting in AD will be like this axially, and the force acting in AC will be something like this. Now for the whole system of the truss, we cannot add the forces which are oriented in different directions directly. Now you'll see that this force will have its components in the horizontal and the vertical direction. Similarly, this force will also have its components in the horizontal and the vertical direction. If you want to look into the equilibrium of this whole system, you have equation like this: summation of force in x direction equals to 0, summation of forces in y direction equals to 0. Therefore, for each bars, we have to obtain the horizontal and the vertical components of the forces. Here, for AD, if this is angle, say beta, then your component here will be F cos beta, and this one will be F sine beta if this force is F. Similarly, this one will also be, if this is beta, then F cos beta, and this one as F sine beta. For AC, you only have force acting in y direction like this, and let's take AB as well. Now AB is oriented like this. Now if you have force acting in this direction, let's say this is F again, and let's say this angle is theta, then the force acting in the x direction will be F cos theta, and in the vertical direction will be F sine theta. Similarly, here also the force acting in this direction will be F cos theta, and this direction will be F sine theta. Therefore, for each of these elements, we can obtain our horizontal forces and vertical forces. If we look into the global system, only then we can add these up to apply the equilibrium. Therefore, we have to formulate a stiffness matrix which takes care of these orientations. Now to do this, what we have to do is we have to take a general case. Let's say we have a truss member like this, which has Young's modulus E, cross-sectional area as A, and length as L. And we can label this as end A and end B. And let the orientation of this be alpha with respect to the horizontal axis. Now here each of these nodes will have 2 degrees of freedom, so this can move in x direction and y direction. This also can move in x direction and y direction. Let this be degree of freedom 1, 2, 3, and 4. As we did before in the bar element, what we do here is we have to find the effect of displacing the truss member at a certain node in a certain degree of freedom with the other degrees of freedom. For example, here if we apply displacement u1 in degree of freedom 1, then we have to find this effect in all the other degrees of freedom, and we have to obtain a relation between these degrees of freedoms. Now this could be effect of this displacement in forces in each degrees of freedom. To do this, what we have to do is we have to apply a unit displacement in each of these degrees of freedoms and calculate the reacting forces in all of these corresponding degrees of freedoms, and at the end add those up like we did in the bar element. Now for case 1, let's say we apply a displacement delta in this direction as equals to u1, a unit displacement. Now due to this unit displacement, what will happen is, if this is the original position of the bar, then if you apply displacement in this direction, your bar will move here like this at this point. Let this be a dash, and this displacement equals to delta equals to 1. Now because of this motion occurring here, you can see here that if you do a 90 degree here, this bar here, the final position of the bar, will decrease its length by delta. Now this is alpha, right? By delta cos alpha. Now this decrease is the delta L, like in the bar element. Therefore this will induce a strain. The strain will be equal to delta L by L, and because of this there will be force occurring in this direction. Now we have to find the components of these forces in all these degrees of freedom. So what we have now is we have this here, this is our A dash, this is our B, and we have our force acting here like this. Now you have to find the components of these forces in all of these degrees of freedoms. Now these forces are induced because of this displacement. Therefore this will give us the effect of displacing a unit in degree of freedom 1 with all the other degrees of freedoms. Now this is also alpha because we are looking into a very small change in angle or a small change in displacement. Since this is a bar element which has gone a displacement of delta L, then the force induced in this bar will be given as AE by L times delta L. Now delta L equals to delta cos alpha. So AE by L times delta cos alpha. Now this delta we have applied equals to 1. You can see here. Therefore, this equals to AE by L cos alpha. Therefore, what we have here is we have our force F as AE by L cos alpha. Now we have to find the components of this force in all these degrees of freedom. So F1 will be equal to, you can see here, F1 be equal to F cos alpha. F2 will be equal to F sine alpha. Therefore, F1 equals to F cos alpha, that equals to AE by L cos alpha times cos alpha, that equals to AE by L cos square alpha. Similarly, F2 will be equal to F sine alpha, that equals to AE by L cos alpha times sine alpha. Again, if you are looking into F3, you'll see here that this force is acting downwards in this angle. Therefore, it will have its components in this direction and this direction. Now this is in opposite to this one. Therefore, this will be minus F cos alpha, and this will be equal to minus F sine alpha. So this is due to displacement of u1 equals to 1. Now similarly, we have to apply a unit displacement in second degree of freedom. Now this will be like this. So you have your bar, you apply a displacement in this direction as delta equals to 1. This is alpha, this is B, this is A, this is E, A, L. Now this displacement will cause this bar to rotate like this. If we draw a 90 degree here, then we see that this one decreases by delta sine alpha equals to delta L. And this will induce a force like this again. This will be equal to F. And then we have to find components of this F in this direction like this. We have taken this one as positive and this one as positive. Now you can see here that your F will be equal to EA by L times delta L, which will be equal to EA by L times delta sine alpha. Now delta equals to 1, therefore it will be equal to EA by L sine alpha. Now you can obtain our forces in all of these degrees of freedoms. So our F1 will be equal to F, this is alpha cos alpha. Now in this case, F is EA by L sine alpha, and then you have cos alpha. F2 will be equal to F sine alpha, which will be equal to EA by L sine square alpha. F3, if you look into the equilibrium of this case, you'll find that F3 equals to minus F1. It will be minus EA by L sine alpha into cos alpha, and F4 will be equal to minus F2, which will be equal to minus EA by L sine square alpha. Now similarly, to find the effects of displacement in degree of freedom 3 and 4, we have to apply delta equals to 1 in this direction and delta equals to 1 in the upper direction. Now if you do this, you'll obtain similar values to this one and this one, but with different sign. You can try it. Let's just make something clear here. In this case here, since we are looking at the effect of displacing the element in the direction of degree of freedom 1, what you can write here is, you can write 1 here. So this means that effect of displacing in degree of freedom 1 in degree of freedom 1, the effect of displacing in degree of freedom 1 on degree of freedom 2, and so on. And here also you can write 2 here. So this is the effect of displacing in degree of freedom 2 on degree of freedom 1, and so on. Now displacing the member in degrees of freedom 3 and 4, what you'll get is, you'll get similar results to this one and this one, but with different sign. You can check this out. Now at the end, we have to add the forces in the x direction and in the y direction. Now what we have to do here is, we have to generalize and we have to find our global force in all the degrees of freedoms. That will be F1 because summation of all the F1 forces due to displacement in I degree of freedom. Now you can see here that we have applied a unit displacement here. Now unit displacement means they are all the stiffnesses in each direction, because by definition your stiffness K equals to force by displacement. Now when you have displacement equals to 1, then it will be equal to force. Now this is like the force required to have unit displacement in the direction of the force applied. So these are all your stiffness values in the corresponding direction. In general, we'll apply a displacement of u1, u2, u3 and u4 in the degrees of freedom. So we have to multiply each values with corresponding displacements and obtain the total force. For example, F1 will be equal to F11 times u1 plus F21 times u2 plus F31 times u3 plus F41 times u4. Now you can write this in matrix form. What we'll have here is, you can exchange these so they form kind of the elements of your matrix, and then you have your u1, u2, u3 and u4. Now if we denote our cos alpha by L and sin alpha by M, then what will happen is, you'll have your values here as L square, this one as Lm, this one as L square, and this one as Lm, and so on. Therefore you can write those values here. Now we have a common here, which is AE by L times u1, u2, u3, u4, and we have our forces F1, F2, F3 and F4. Now this is our required equilibrium equation, and this is the required stiffness matrix for a truss element. Please be careful here because the sign convention we are taking here is anti-clockwise and the angle here is made with the horizontal. So when you are solving a problem, just be careful and use anti-clockwise angle with the horizontal to be substituted in these equations. Now let's look into a numerical example. Let's say we have a rod like this, and this is horizontal axis, that's the vertical axis, and let's say this angle here is 30 degrees. You have your area as 2 inches square, length as 60 inch, and you have your elastic modulus as 30 into 10 to the power 6 psi. Let's say this is node 1 and this is node 2. Now similarly, we have another problem. Here you have to find your stiffness matrix such that this one is kind of flipped, and this is node 2 and this is node 1, and this is your angle 30 degrees. This is your x, this is your y. Now you have to find your global stiffness matrices for these two cases. The stiffness matrix will be given by, now for the first case, what is your alpha? Your alpha equals to, if this is your x-axis and this is your inclined element, bar element, then you have to take your angle in an anti-clockwise direction with the x-axis. Now since you have node 1 here, we are looking from node 1 to node 2. That's always the case. So this will be equal to 30 degrees. Now let's look at our case 2. Now here you will see that this is our node 1, this is our node 2. Then what will happen is that you have to shift your axis to node 1, because we always look from node 1 to node 2, and then you have to get your anti-clockwise angle. Now your angle is always taken as anti-clockwise from the x-axis, so this will be your angle, not this one. So this angle will be, therefore alpha for this case equals to 210 degrees. Now what you have to do is you have to find your L, that is equals to cos alpha, that equals to cos 30 degree for this one. M equals to sine alpha, that equals to sine 30 degree. And for this one, you have to find your L, that is cos 210 degrees, and M as sine 210 degrees, and then substitute your values into this equation and obtain your stiffness matrix. You'll find that the matrices will be different. This is just to show the importance of the sign convention, because we derive formulas based on certain standard orientation. You can try this and find the values. So for our next example, let's say we have a truss that is like this. And let these angles be 45 degrees and 45 degrees. Let's say this is 10 feet and this is also 10 feet. And let's say we have a force here acting downwards, and let it be 1000 pounds. And let the elastic modulus be 30 into 10 to the power 6 psi, or area be 2 inches square for all of these elements. Now the question here is to find the displacement at this point here. Let's label our nodes. Let it be, this one be 1, 2, 3, and this one be 4. Displacement at node 1 in x and y direction. So this can be our x direction and this is our y direction. Now this is the problem. So first, in the procedure, what to do is we have to find our angles for each of the element. So we can name our elements as, let this one be element number 1, this one be element number 2, and this one be element number 3. Now we form a table where we write our element, its corresponding nodes, their lengths, and their angles alpha, and then L that equals to cos alpha, and M that's equals to sine alpha. Now for your element number 1, which is this one, you can see that the angle made with the horizontal x-axis, but this is 90 degree. Therefore this will be 90 degree, and nodes will be 1 to 2, and our length is 10 feet. Therefore our L will be cos 90, that equals to 0, and M will be sine 90, that equals to 1. Now we have element number 2. So nodes corresponding to this one are 1 and 3, 1 to 3. We're looking from here to here, and then the length will be 10 divided by sine 45, that will be 10 root 2, and the angle here is this one, so that is 45 degrees. Therefore L equals to 1 by root 2 and M equals to 1 by root 2. For our third element, which is this one here, we have 1 to 4, and our length is 10 feet. Alpha is, you can see here that this is oriented in the x direction, therefore alpha equals 0 degree. Now your cos, your L will be equals to 1, and your sine or M will be equals to 0. Now these are your values for each of your members. Now we have to form our stiffness matrix for each of these elements and then combine them together to form the global system. Now our second step will be to find our stiffness matrices. This is our general equation for the stiffness matrix. Now for element 1, your K1 will be equal to AE by L, and L is 10 feet. You have changed that to inches because this is in PSI, so this is PSI, that's inch square, and your length must be in inches, so it will be 10 times 12 inches. Then you have to put the values of L square and Lm in this matrix for your element number 1. So here we have L equals to 0 and M equals to 1. So for this case, now for your K2, K3, now here, like we did in the bar elements, we have to label our degrees of freedom. Now in this case, what we have to do is we have to label our degrees of freedom 2, 3 and 4. Now in all of these cases, what you have to do is you have to label the degrees of freedom. So for this case, each point can move in 2 directions. Now for this one, it can move in 1x. Let's say this is x and this is y. This will be 1y. So this degree of freedom is 1x, this is 1y, and this one is 2x, this is 2y. This one will be 3x, 3y. This one will be 4x and 4y. Or you can label this as 1, 2, 3, 4, 5, 6, 7 or 8 as per your convenience. So for me, I'll write here 1x, this will be 1y, this will be 2x and this will be 2y. So 1x, 1y, 2x, 2y. For element number 2, it will be 1x, 1y, 3x, 3y. This will also be 1x, 1y, 3x and 3y. Now for the other one, for element number 3, it will be 1x, 1y, 4x, 4y, 1x, 1y, 4x and 4y. As you did earlier, that this one is 1, 2, 3, 4 while you're obtaining the stiffness matrix. So in here it will be 1x, 1y, 2x and 2y. This is the similar configuration. Now we have to add these up to form our global matrix. Now this matrix is also based on your degrees of freedom. Let's write our global matrix, which will be equal to Kg. Now for this case, what we have to do is we have to write all of our degrees of freedoms. So it will be 1x, 1y, 2y, 3y, 4x and 4y. Here also 1x, 1y, 2x, 2y, 3x, 3y, 4x and 4y. Now to fill this, you have to look at 1x, 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 1x. We can see here that there are 3 values of 1x. You just have to add those up. So what you get here will be 0 plus 0.5 plus 1. Now for the next one, this is 1y and 1x. So 1y, 1x will be this one, this one and this one. You just have to add those up and you will get 0.5. Similarly for 2x and 1x, it will be 0, and 2y and 1x, it will be 0. For 3x, you can see that this is minus 0.5, 3y minus 0.5, and this one as -1, and this one as 0. Now let's look at the second row. Now second row will be, I just made a mistake because we have this as common here, this as common here, and this as common here. You can see that there is extra √2, which I have to put it in. So here it will be √2, √2. So at the end, what we'll have here is 2 times 30 times 10 to the power 6, 10 times 12 as a common. Now this one will be 0.5 by √2. This one also √2 by √2. Now for the other one, 1y, 1y, so it will be this one, and this one, and this one. So it will be 1 plus 0.5 by √2 plus 0. Similarly for 2x it will be 0 and then -1. For 3x it will be minus 0.5 by √2 minus 0.5 by √2, and this will be equal to 0 and 0. This is our first row, this is our second row. Now for the third one, we have to look into 1x and 2x. So it will be this row here. We have 0.5 by √2 as 0.354. So write 0.354 here. Now for the third row, which will be 1x and 2x. For the 2x, what we are going to do is you can look here. This one will be 0. Now 1y, 2x will also be 0. Now 2x, 2x, it will be 0. 2x, 2y. Now for 2x, 3x, this is also 0, 0, 0, and 0. So this is our third row. For the fourth one, we're going to look into 2y. So it will be 0, -1, 0, -1, and then 0, 0, 0, 0. Now for 3x, we have to look into this row here. Now what you get here is minus 0.354, minus 0.354, and then 0, 0. This one here, 3x, 3x, it will be 0.5 by that, so it will be 0.354, 0.354, and then 0, 0. For 3y, we have to look into this one. So it will be minus 0.354, minus 0.354, and then 0, 0, and then 0.354, 0.354, and then 0, 0. Now for 4x, we have to look into this row here. So what we have here is -1, 0, and then for 2x, 2y, we don't have any relation, it will be 0, 0. For 3x, 3y also we don't have any relation, it will be 0, 0, and then we have 1, 0. For 4y, we have to look into this one. We have 0, 0, and here no relation, here also no relation, and here we get 0, 0. So this is our global stiffness matrix, and this one we have as common. I think this one, we'll just have to do a correction here, and this one is positive, because this is m square, and m for this one is 1, so this will be positive. When you go down here, then this will also be positive. So this is our global stiffness matrix. Now what we have to do is we have to write our global equilibrium equation. We have to write our forces in each of those directions. What to write here is F1x, F1y, F2x, F2y, F3x, F3y, F4x, F4y in all the degrees of freedoms. Now this will be equal to your global stiffness matrix times U1x, U1y, U2x, U2y, U3x, U3y, U4x, and U4y. This is our equilibrium equation for the whole system. Now here you have to put the boundary conditions. You can see here that our 2x and 2y at this point, 3x and 3y at this point, and 4x and 4y at this point are all 0 because they are constrained to move in those degrees of freedoms. Therefore, when you go down here, you put this one, this one, this one, this one, this one, and this one as 0. And when you look at the forces, you'll see that in the degree of freedom of F1y here, we have load applied. That load is equal to 1000 pounds, but in opposite direction. So your F1y will be equal to minus of 1000 pounds. And for the x direction here, F1x, we have no load applied, so 1x equals to 0. But for the other degrees of freedoms, you'll have your reaction forces. Now for this case, what you write here is, we write our F1x equals to 0 and F1y equals to minus 1000 pounds. Therefore, our equation will reduce to, since we know the left hand side values of F1x and F1y, what to write here is F1x, F1y equals to your stiffness matrix for these two degrees of freedoms. So this will be for degree of freedom 1x and 1y, and then we have U1x and U1y. Now here, this will be equal to 0, this will be equal to minus 1000, and your kg, your stiffness matrix for this case will be 1x and 1y. So we just have to look into this matrix here. So what to get from there is 1.354, 0.354, 0.354, and 1.354 into U1x and U1y. So now you can solve for your U1x and U1y. We have a common out, which is this one. This equals to 5 into 10 to the power 5. So we have this one times of 5 into 10 to the power 5. 1 by 5 into 10 to the power 5 inverse of this matrix times of 0 and minus 1000. Now when you solve this, what you'll obtain will be 0.414 1.59 into 10 to the power minus 2 inches. So this is our solution. Now here you can see that your u1x moves in the positive x direction and u1y moves downwards, and this is in the direction of the force applied. So this is our required solution. Now if you want to find your reaction forces, then what you got to do is you have to substitute these values back into this equation and solve for your forces. If you want to look into another example, so you can go into another playlist which is on the abacus modeling, and there you can go to chapter 1, Truss modeling. So today we learned about the stiffness matrix of an inclined bar element, and we did a numerical of a truss in which we obtained the displacements under the applied loading. In this case, you just have to be careful about your node numbering and your alpha. And while you are forming your element matrices, just be careful on the degrees of freedoms. And also, while forming your global matrix, be careful on the degrees of freedom, because you have to add those degrees of freedoms which are similar. So this is it for today. In our next lecture, we will learn about beam element, where we will obtain the stiffness matrix of a beam element and do a numerical. Thank you for watching till the end. See you next time. Cheers.